Imagine taking just a thick, heavy bucket of industrial rig grease,
Okay.
slathering it onto a massive steel drill string that is about to be subjected to like 500-degree Fahrenheit heat and crushing geological pressures.
Yeah, really hostile environment.
Exactly. And then taking that exact same grease and just dropping it directly into the pristine, icy waters of the Norwegian North Sea.
Wow.
And knowing for a fact that it won't harm a single microorganism.
It's just a phenomenal contrast. I mean, you have this ultimate collision between one of the most violent, unforgiving mechanical environments on Earth,
Yeah.
and then, on the other hand, one of the most fragile aquatic ecosystems out there.
Welcome to our deep dive, everyone. Today, we are taking you with us to explore a single, highly specific technical document.
Yeah, we're really getting into the weeds on this one.
We totally are. We're looking at a data sheet from Jet-Lube for a product known as NCS30 ECF, which is a drill string compound.
Right.
Our mission today is to look past all the dense technical jargon, past the friction factors and toxicity metrics on this sheet, to uncover what is basically a massive, almost invisible revolution happening in heavy industry.
It really is.
We want to understand how modern engineering is adapting to meet like the most rigorous environmental standards on the planet without sacrificing even an ounce of performance on the rig floor.
Yeah, and to really grasp the scale of the engineering challenge here, you have to picture that split screen for a second.
Okay, paint the picture.
So on one side, you have the deafening, gritty reality of a high-tech rotary drill rig.
Right.
You've got these massive steel pipes. They're just spinning under unimaginable force. And then on the other side of your mental screen, you have those crystal clear North Sea waters.
The contrast is just crazy.
It is. And historically, keeping those steel threads from fusing together under all that extreme friction meant you had to pack your drill compound full of heavy metals.
Like what? Lead.
Yeah, lead, zinc, copper, all of that.
So basically, metal scraping against metal needs a barrier. So the old school approach was just to like load up the grease with softer metals to take the damage.
Exactly.
But that leaves you with a highly toxic sludge, right?
Incredibly toxic.
Okay, let's unpack this. Because this Jet-Lube NCS30 ECF datasheet explicitly states, like right at the top, that it is a premium quality non-metallic compound.
Right, non-metallic, that's the key.
Instead of heavy metals, it says it relies on chemically inert fibers paired with extreme pressure and anti-wear additives.
Yep.
And then it notes the base grease is made from a synthetic and vegetable fluid type using complex thickeners.
Which is a huge shift.
Well, no, I have to push back a little here.
Okay, go for it.
The density is listed as 11.35 pounds per gallon. Its specific gravity is 1.36.
That's very heavy.
It's incredibly dense. I mean, it sinks in water. So we are talking about a heavy industrial paste, but it's vegetable-based.
Yeah, I know, it sounds wild.
Why use a synthetic and vegetable fluid base for something tasked with lubricating millions of pounds of steel that literally crushes rock? I mean, isn't that like bringing a salad to a knife fight?
That's a great way to put it. But what's fascinating here is how the chemistry completely rewrites the rules of tribology.
Tribology being like the science of friction and wear, right?
Exactly.
Yeah.
And you aren't wrong to be skeptical of a vegetable base. Traditional vegetable oils, they actually have fantastic natural lubricity.
Oh, really?
Yeah, but their thermal stability is notoriously poor. I mean, they would incinerate or just shear apart instantly under the friction of a deep water drill string.
Which is bad.
Very bad. So that is where the synthetic component and those complex thickeners come into play.
Okay, so how do they work together?
Well, the thickeners essentially act as a microscopic three-dimensional scaffolding.
Scaffolding, okay.
Right. They lock the naturally biodegradable vegetable and synthetic oil molecules into this structural matrix, and that shields them from immediate thermal and mechanical breakdown.
Oh, wow. So the complex thickeners are basically building a protective fortress around the vulnerable vegetable oil, allowing it to survive the pressure.
Precisely. They engineer the structure so the fluid can do its job without being destroyed.
That's incredibly smart.
It really is.
Yeah.
And the real brilliance of this formula is the substitution of the heavy metals with those chemically inert fibers.
Because, again, no lead or copper.
Right. When you make up a rotary shouldered connection, you are dealing with thousands of foot-pounds of torque.
Yeah.
The threads are under massive compressive stress, and they naturally want to bind together. It's a process called garring.
Galling, right, where the metals basically cold weld to each other.
Exactly. And soft metals like lead used to act as a sacrificial layer between those threads. But these inert fibers achieve the exact same goal through physical geometry rather than, metallic smearing.
Physical geometry.
Yeah, under extreme pressure, these fibers compress and they mat together, forming this dense, non-metallic physical matrix.
Wait, so they act almost like a high-tech synthetic joint cartilage for the steel pipes.
That is a highly accurate way to visualize it, yeah.
Yeah.
They keep the metal surfaces physically separated, which provides that crucial extreme pressure protection.
Okay, I'm tracking.
But because the fibers are chemically inert, they don't react with the steel, they don't break down into toxic byproducts, and they certainly don't pose a heavy metal poisoning risk if they're, introduced to the environment.
Right.
It's just a fundamental shift from brute forcing lubrication with toxic materials to utilizing smart structural chemistry.
And the data sheet notes the color is beige,
Yes.
which I think visually separates it from that old black metallic sludge we are so used to seeing on the rig floor.
It really does stand
It
out.
looks different because it's fundamentally operating on a completely different chemical paradigm.
Exactly.
But if this vegetable-based, non-metallic compound is so structurally advanced, it still has to survive the actual daily realities of offshore drilling, right?
Oh, absolutely.
I mean, it isn't just pressure it has to worry about.
The environmental realities of a rig floor are a nightmare scenario for any protective coating. I mean, you are dealing with vast temperature swings, constant corrosive exposure, chemical assaults from downhole operations.
Yeah, and the survival metrics on this data sheet really paint a picture of that hostility.
They're pretty intense.
The testing shows the service temperature ranges from -10 degrees Fahrenheit, so like -23 Celsius, all the way up to a blistering 500 degrees Fahrenheit, or 260 Celsius.
And if you look closely at the thermal breakdown thresholds,
Right.
the dropping point, which is the temperature where the thickener matrix finally fails and the grease turns to liquid, is listed as greater than 450 degrees Fahrenheit.
Wow.
And the flash point, where it would actually produce enough vapor to ignite, is also over 450 degrees.
That's insane. And then you have the corrosion testing, which, quite frankly, sounds like a torture chamber.
It really does.
I mean, it says it survives a 5% sodium chloride salt fog for over 2,000 hours and a highly concentrated 20% salt fog for over 750 hours.
It's incredibly resilient.
And after all of that, it maintains a copper strip corrosion rating of 1A, which is the highest possible rating for non-corrosiveness.
Yep.
It also holds an NLGI grade of 1 to 1.5, keeping a specific penetration rating between 300 and 330 at 77 degrees.
Right, which means it stays workable.
So I have to ask, are these extreme numbers, like subjecting a grease to 2,000 hours of concentrated salt fog, just an industrial marketing flex? Or does a compound actually need that level of endurance to function?
It's not a flex at all.
Yeah.
Those metrics represent absolute baseline survival for offshore operations.
Really? Baseline?
Yeah. Think about it. A rig is essentially a massive steel island sitting in a highly corrosive saltwater bath.
Oh, true.
That 2,000-hour test in a 5% sodium chloride fog, that equates to over 83 solid days of the compound being continuously blasted by aggressive ocean spray.
83 days. Wow.
If a drill string compound breaks down under those conditions, the pin and box threads on the drill pipe will flash rust sitting in the racks before they're even picked up by the top drive.
Oh, so it protects them while they're just waiting to be used.
Exactly.
It also explicitly highlights superior adhesion to wet steel surfaces and that it resists water wash-off while withstanding invert and high pH muds.
Yeah, and the resistance to high pH muds is a really critical detail here.
Why is that?
Well, invert emulsion muds and highly alkaline drilling fluids are chemically aggressive enough to saponify a standard grease.
Saponify, like turn it into soap.
Basically, yeah, turning it into a useless soap that just washes right off the connection.
Oh, man, that's not what you want.
Not at all. But the complex thickeners in NCS 30 ECF are engineered to resist that chemical conversion. They maintain that dense 11.35 pounds per gallon structure, adhering stubbornly to wet joints.
Right.
And that 1A copper strip corrosion rating proves that even while baking at hundreds of degrees downhole, the compound itself isn't turning acidic.
So it's protecting itself, too.
Exactly. It remains entirely stable, acting as an impervious chemical and physical fortress for the steel threads.
Which brings us to a really fascinating paradox.
Okay.
We have a product engineered to be incredibly stubborn. It refuses to melt downhole, it refuses to succumb to alkaline drilling muds, and it aggressively resists water wash-off.
Right.
But this is an offshore operation. Eventually, through routine maintenance, breaking out pipe, or just accidental deck spills, this stubbornly adhesive compound is going to interact with the ocean.
It's inevitable, yeah.
Right. It survives the ocean water, but does the marine environment survive the compound?
Well, that is the ultimate test of this new industrial philosophy.
Yeah.
Creating an indestructible grease is easy if you don't care about toxicity.
Good point.
But creating an indestructible grease that leaves no ecological footprint, that is a monumental achievement.
Here's where it gets really interesting. The datasheet emphatically states that NCS30 ECF is biodegradable, non-bioaccumulative, and non-toxic to all tested life forms. It carries an NSF-H2 registration. And to back this up, they highlight that it contains absolutely no detectable, leachable, volatile organics.
It's just huge.
Right, which they verified using a highly specific independent third-party test, the EPA test method, 1311 TCLP, specifically SW8468260B.
Quite the mouthful.
It really is. Now, the term biodegradable gets thrown around constantly in consumer marketing.
Oh, all the time.
So how does a hyper-specific EPA test like 1311 TCLP prove to rig operators that this isn't just corporate greenwashing?
Well, if we connect this to the bigger picture, industrial biodegradability testing operates in a completely different universe than, say, consumer plastics.
Okay, how so?
The EPA 1311 TCLP, which stands for the Toxicity Characteristic Leaching Procedure, is designed to simulate a worst-case environmental scenario.
Like what?
It tests what happens if you dump a material into a landfill and let aggressive acidic fluids wash over it for an extended period.
Oh, wow.
Right? The goal is to see if any hazardous volatile organic compounds will detach from the chemical matrix and leach into the surrounding water table.
And the results here are non-detected.
Exactly. Meaning the chemical matrix is utterly stable. There are no hidden toxic solvents waiting to escape when the compound is exposed to the elements.
That's amazing.
But the more profound environmental metric you mentioned earlier is non-bioaccumulative.
Right. What does that actually mean?
Well, a substance can technically be biodegradable, but still cause massive ecological damage if it accumulates in the lipid tissues of organisms as it moves up the food chain.
Oh, like heavy metals.
Heavy metals are notorious for this, yes.
They get absorbed by plankton, eaten by small fish,
Oh.
then larger fish, and the concentration of the toxin magnifies at every step.
Because the biological pathways cannot break down or excrete the heavy metals.
That makes sense.
But by utilizing a synthetic and vegetable ester base with chemically inert fibers, this compound avoids that entirely.
So marine life can actually process it.
Yeah. The chemical structure is something that marine metabolic pathways can recognize, process, and clear naturally. It does not magnify in the food chain.
Wow. And the ultimate proof of that environmental safety seems to be the international certifications it has unlocked.
Oh, for sure.
The sheet proudly displays its OSPAR Commission HOCNF ratings.
Right.
That stands for Harmonized Offshore Chemical Notification Format. It states that this was the very first compound to achieve a yellow rating in the Norwegian sector of the North Sea.
Which is a huge deal. The Norwegian environmental regulations are arguably the most stringent in the world.
Really?
Oh, particularly when it comes to the North Sea and the Barents Sea.
Why the Barents Sea specifically?
The Barents Sea is a highly sensitive, tightly regulated ecological zone critical for global fisheries. Achieving a yellow rating there means the compound has been scrutinized down to its molecular bonds and deemed safe for use in an almost pristine environment.
That's incredible. It also achieved a substitution warning-free HOCNF rating and an E classification in the UK sector, which simplifies PON15B applications. The datasheet even lists its specific Denmark PR number, 3456194. I mean, it's fully vetted across the most heavily regulated waters on the planet.
And those classifications tell rig operators that they are utilizing the absolute safest option available.
Right.
The regulatory bodies aren't issuing warnings requiring them to substitute it for a greener alternative because currently the chemistry doesn't get much greener than this.
Okay, so we have established that this beige paste is a mechanical fortress that happens to be entirely ecologically benign.
Yes.
But the deep dive doesn't end there. We have to look at how this material integrates into the complex, highly sensitive technological ecosystem of a modern drill rig.
Right, because the mechanical symphony on the rig floor requires absolute precision.
Symphony's a good word for it.
It is.
Yeah.
And the datasheet points out that NCS30 ECF provides excellent protection against seizing and galling on high chrome or nickel alloys.
And those are specialized metals, right?
These are incredibly expensive, highly specialized metals that are notoriously difficult to lubricate.
It says it is designed for standard rotary shouldered connections like tool joints and drill collars.
Yeah.
But it also specifically highlights its compatibility with premium or proprietary threads, calling out double-shouldered connections and wedge thread, which is a trademark of Tenorus Hydro Company.
Right.
It can even be used on non-interference tubing threads if the torque is compensated.
And just for context, wedge threads utilize a highly complex interlocking geometry to bear loads and create seals.
So they need a specific type of grease.
Exactly. They require a lubricant that provides a perfectly even, predictable layer of physical protection without interfering with the mechanical mating of the steel.
So what does this all mean?
Wow.
Actually, the detail that really got my attention regarding integration is the line stating it is non-conductive for MWD applications.
Yes.
MWD is measurement while drilling, right?
That's correct.
The analogy I immediately go to is noise-canceling headphones.
Okay, I like that.
Is using this non-metallic compound essentially like wrapping a noise-canceling material around the drill string to ensure the physical grease doesn't scramble the digital telemetry transmitting from the bit.
This raises an important question about the hidden variables in downhole telemetry, and your noise-canceling analogy is structurally perfect.
Oh, awesome.
Because measurement, while drilling, relies on sending continuous data like directional surveys, gamma ray logs, pressure readings from the bottom of the hole back up to the surface.
And how does that data actually travel?
This is often done via electromagnetic telemetry or mud pulse telemetry.
Okay.
So if you load your drill string connections with a grease packed full of metallic flakes like copper or zinc, you are introducing highly conductive materials directly into the signal path.
Oh, I see. You are basically painting the connections with random electrical pathways.
Exactly. It creates electrical bridges that can short out sensors, attenuate electromagnetic signals, or introduce massive amounts of interference.
Which would ruin the data.
Totally ruin it. But by relying on a nonmetallic base and chemically inert fibers, the compound remains electrically non-conductive.
So it does its job without causing interference.
It performs its massive mechanical duty bearing thousands of pounds of torque while remaining completely invisible to the digital brains of the drilling operation.
It's doing the heavy lifting without making a sound.
Precisely.
And speaking of the mechanical lifting, there is a very strict directive on this sheet regarding how the rig crew actually applies the torque.
Oh, the friction factor.
Right. The friction factor is listed as 1.0 relative to API RP5A3 Annex 1.
Yes.
And the specific instruction is: start drilling with standard friction factor times torque. But if breakout torques are higher than makeup torque, use the extra 10% factor.
That directive is a brilliant example of translating complex tribology into practical rig floor operations.
So.
Well, a friction factor exactly 1.0 is basically the holy grail for a rig crew.
Really? What?
It means the compound perfectly matches the baseline torque resistance expected by API standards. When the iron roughneck applies a 30,000 foot-pounds of makeup torque, the connection receives exactly what is intended.
Because there's no weird math to do.
Exactly. The crew doesn't have to calculate arbitrary mathematical multipliers to compensate for a grease that is too slick or too sticky. It guarantees operational consistency.
But the Earth always has a vote, which is where that 10% rule comes in.
Exactly. When you trip pipe out of the hole, you have to break out or unscrew the connections.
Right.
And downhole temperatures and immense cyclical loading can cause the threads to wedge together even tighter than when they were made up on the surface.
Which makes them harder to unscrew.
Much harder. So if the driller notices that the breakout torque is exceeding the initial makeup torque, the data sheet provides an immediate operational safeguard.
The extra 10%.
Yep. By adding a 10% torque factor on the next makeup, they ensure the inert fibers are preloaded to withstand that specific downhole thermal expansion, preventing thread damage.
It is an incredible amount of science, foresight, and real-time operational feedback packed into a product that, honestly, most people outside the industry would dismiss as just a bucket of beige sludge.
It really is the perfect synthesis of chemical engineering and operational reality.
Absolutely. As we wrap up this deep dive for you today, it is worth stepping back to look at the massive shift in industrial philosophy that this single data sheet represents.
It's a huge shift.
Jet-Lube's NCS30 ECF manages to seamlessly bridge Two worlds that used to be completely at odds.
Yeah.
I mean, it provides the extreme mechanical protection necessary to drive millions of pounds of high-chrome steel through solid rock, utilizing chemically inert fibers to withstand 500-degree heat and crushing pressures without scrambling delicate downhole digital telemetry.
You're doing so much at once.
And it accomplishes all of this while remaining completely non-toxic, non-bioaccumulative, and safe enough to achieve a yellow rating in the hyper-regulated waters of the Norwegian North Sea. It proves that heavy industry and deep ecological responsibility are no longer mutually exclusive concepts.
You know, I want to leave you with a final thought to mull over.
Okay, let's hear it.
We spent this deep dive analyzing a simple thread compound that was fundamentally re-engineered at the molecular level to remove heavy metals, survive 83 days of corrosive salt fog, and protect marine ecosystems.
Yeah.
If something as seemingly mundane and invisible as the grease on a drill pipe is quietly undergoing this massive, highly engineered environmental revolution,
Right.
what other invisible industrial materials hidden deep inside the infrastructure of our daily lives are going through the exact same silent, remarkable transformation right beneath our feet?
Man, it completely changes how you view the hidden gears of the world. Thanks for coming along with us on this deep dive.